slides. In this video, we're going to be talking about introductory discussion on identifying the main types of machine learning and the fundamental differences between them. The second question that we have in this video is the gradient descent and how does it optimize machine learning models, and how the choice of learning rate influences the speed and the stability of convergence. And the third topic for this video is the architecture of a convolutional neural network. Let me move my picture out of the way. And the roles of the convolutional layers, the pooling layers and the fully connected layers. For this video, we're going to use, as I said, PowerPoint slides, but also we have a whiteboard. And all the references are in the list of references here. Let me maximize this into the full mode. Starting with the first topic, and maybe this video is just going to be on the way, so I'm going to close the video. The main types of machine learning are supervised learning, unsupervised learning, reinforcement learning, and there is also a merging combination of those models. But the main three types of machine learning are supervised, unsupervised, and reinforcement learning. The main difference is that the supervised learning is trained on labeled data and it's used for classification and regression. The unsupervised learning is trained on unlabeled data and usually discovers hidden patterns in the data. And the reinforcement learning, it's where agents learn by trial and error, and it's guided by rewards and penalties that usually it's applied in robotics, strategy, and adaptive security. The second topic that we have here is optimizing models with gradient descent, and this is probably going to make a lot more sense when we look at the drawings on the whiteboard. But the optimizing model with gradient descent, it's a process that minimizes the loss function and to adjust the model steps with the weights. And the first step is that you compute the gradient, that's the slope of error surface. Second step is that you update the weights in the opposite direction of the gradient, and you have to repeat this process until you get the convergence, the minimal error, and the minimal error is here at the bottom of the slope. The learning rate controls the step side. If it's too high, it's unstable and might overshoot. So this here, it's an example of overshooting. And if it's too slow, then it's getting into a risk of getting stuck and never reaching the point. Basically, you're going to have too many steps. And for this, you need to adapt adaptive methods like Adam and adjust the learning rate. For the convolutional neural network architecture, the key components, and this is just one diagram out of many that we're going to be looking. Sometimes when you get into more complicated aspects, it's easier when you have different visualizations because that would make more sense to you. The convolutional layers are when you detect the local patterns, the edges, the textures, and here is when you apply filters and kernels. The pooling layers is the downsample feature maps that reduce the dimensionality and increase the robustness. And the fully connected layers is when you integrate the extracted features for final classification. The implications is usually in image recognition, video analysis, adversarial robustness, and you can target many attacks with this. Here we have a list of references of the most famous articles in this sphere. So in terms of the types of machine learning, and you have a reference here with which is a link, but also it's if you type that in Google, it will show up because that's a unique reference. For the gradient descent and learning rate, here we have one of the leading papers. And for the adaptive learning, here's a link to the Adam paper that's on arXiv, so it's open source, publicly available. For convolutional neural networks, here we have one of the seminal convolutional neural network papers that they're based for model deep learning. We have a second paper, which is the CNN convolutional neural network architecture. And additional papers that you should be familiar with include, so Godfellow is one of the leading authors, but I couldn't find the. So this is a very authoritative reference, but I couldn't find the correct reference number. If you type Godfellow, you would find the actual paper. And here we have the links that we used for these slides. Now let me share the screen so we can review the same thing but from a slightly different perspective. Let's see what kind of pen is best used for this drawing. This should open here. Maybe this one. And let's change the color. As we said, we have supervised learning, which is based on labeled data. We're going to have multiple examples of this, but imagine that you have apples and pears, and then you tell the diagram, the algorithm, that those are the two things that you're searching for. Well, clearly the algorithm would be able to identify in large data sets. Unsupervised learning is when you have unlabeled data. Here, imagine that you have a whole market of different fruits and vegetables, and you want to categorize them into different and to identify different categories and to identify what is in each, what is representative in that specific market. Is it lemons? Is it apples? And the third would be reinforcement learning, which is the most interesting aspect of artificial intelligence at the moment, because this is where agentic AI emerges. With reinforcement learning, we have an agent, which is usually portrayed as a robot, that interacts with the environment and then learns from the environment and gets a specific reward for performing the tasks correctly, and then reinstates this whole loop over and over again. So it constantly learns from the environment. That means that it's both. It's supervised, unsupervised, but it's a little bit more than the sum of those two things. Now, let's look at the gradient descent. This is a diagram that I have prepared, but in the third section of the presentation, I'm going to show you different aspects and different images that other people have prepared, and that might make more sense to you. So the gradient descent is a method for teaching machine learning models by making small adjustments. So those are the small adjustments that is referring to the parameters, or also known as the weights. So those are known as the weights. So imagine that the model error is a landscape. Usually it's described like a landscape of different mountains and hills and valleys, for example. And the goal is to reach the bottom of the deepest valley. That is the point where the model makes the least mistakes. And at each step, the gradient descent, so those are the steps, the gradient looks at the slope of the landscape and then moves to the parameters to the opposite side of the slopes. And if you repeat this process, that makes the model prediction gradually more accurate as the parameters descend towards the minimum error. So the learning rate here, if it's the learning rate needs to control the size of each step. So if the learning rate is too low, then the steps are too large. So if the learning rate is too high, then it might overshoot, so the valley, and bounce back. And that means that, let's say you have one step, second step, third step, fourth step, and then you overshoot, you're never going to reach this the optimal point. So that is the simplest explanation of the gradient descent, and we're going to look at more complicated explanations. Now let's look at a very simple explanation of the last question that we had here before we move into the more technical aspects of the presentation. So with the convolutional neural networks, this is just a type of deep learning model that is designed for images, but also is used in video, speech, and other data. And think of it as a pipeline. of things that gradually turn raw pixels into meaningful patterns. So in convolutional layers, for example, these act like filters. They can scan over the image to find small parameters such as edges, corners, or textures. So stacking multiple convolutional layers would allow the network to build up from single shapes to more complex objects. And then you have pooling layers. Those are that will shrink the size of the data by keeping only the most important information, and then they will disregard the details. And this makes the network faster and reduces the memory use. So it makes the less sensitive to small changes in the input. So in the next images, we're going to be seeing how those different layers occur. But this is just a simple explanation that first we have the convolutional layers, then we have the pooling layers, and then you have the fully connected layers at the end. So this is where all the extracted features are connected together, and these layers combine everything from the network and then make the final predictions, such as cat, dog, or whatever. It's a car, for example, here. So that's the most basic explanation of these three concepts. And now let's go back to look at this from a slightly different perspective. So first we looked at the PowerPoint slides, then we looked at this from the whiteboard aspect, and now let's see what I have prepared. Oh, by the way, I forgot to introduce myself. My name is Petar. I work for the University of Oxford. I'm based in the Department of Computer Science. This is my whole bibliography here. If you want to know more about me, I also work for the Turing Institute. I have an association with them. The Turing Institute is the leading AI institute in the United Kingdom. I teach for Pearson's and O'Reilly, and this Pearson's and O'Reilly is the largest publisher in the world. They have more than 1,600 courses. Quite a lot of them are mine. So I have a course now on 16th of September on the AI attack surface. I teach agentic AI and cybersecurity risks. I have bootcamps, books, and various different recorded papers. I also teach for the Swiss Cyber Institute. So my next workshop is on the 17th of September. That's in 5 days. I do have a whole set of books that you can get online and read them on this specific topic. They're fairly recent, most of them. And there's also a whole list of journal papers that I have published. They're in open access, freely available. So if you click on that link, you don't have to pay anything. It will open the actual paper. And that's because the University of Oxford has paid the open access fees. And those are freely available papers that you can read just by typing my name in Google. Now, let's look at the explanation of the three key questions that we have, but let's look at examples from journal papers and how other people have explained it. So this is the first question that we had. So let's just remind ourselves what was the first question. The main types of machine learning: supervised, unsupervised, reinforcement, and semi-supervised learning. So for this, I'm going to use a paper from Jing Peng, which is included in the references below. But they described it as the machine learning being, but by the way, there's machine learning and there's symbolic AI, which is based on pure logic. And now we're working towards combining into neurosymbolic AI, where you have neural nets machine learning basically with symbolic AI. But symbolic AI is a different version of artificial intelligence. It was the original form based on pure logic, and that didn't really prevail. Now we're using machine learning mostly. So we have the supervised learning, where the model is trained with data. You can use this for classification and regression. So you can classify things into groups like here, or you can use just the linear regression. Unsupervised learning is the model when you have unlabeled data, and this is where usually you cluster data. I compared this with the market, so you have all the data from the market, and then you would feed this to the algorithm, and the algorithm would cluster this into, let's say, apples, pears, lemons, and then you would know what's in the data, um, what kind of the entry points there in this. And the final was reinforcement learning, where the model makes action based on the environment that then receives reward, and the reward is crucial here, but quite often I get asked the question, who determines the reward? Well, the designer of the system, the software developer basically. But this is how it operates. So first you have the action, and then it learns from the environment, the state, and then the model agents gets feedback on the state and then repeats the action. So this process is continuous, and that's why reinforcement learning is probably one of the strongest algorithms that we currently have, because it will constantly learn from the environment. Now, looking at the different types of machine learning, for this I'm going to use the article from AJBO, Nisha, Arya. And this is another example of supervised learning, when you have a supervisor that provides training data but also provides the desired output, and the combination of those two creates the algorithm. Then you feed the raw data to the algorithm, which already has the desired output, so it knows what's apple, what's pears. That has been labeled already. So this has been fed with the training data, saying that the apples with a label, those are the apples. And different examples of apples, that's pears, different examples of pears. Lemons, different examples of lemons, all labeled as lemons. And once you feed the raw data from, let's say, the market for apples, pears, and lemons into the algorithm would be able to process, and then it would output that and tell you, you have 10 apples, you have I don't know how many lemons, and that's all listed and analyzed. The second example that we said was unsupervised learning, where the raw data is fed into interpretation before it's fed into the algorithm. Then it's processed and the output emerges the same, like with the supervised learning. But this is an example of when you have data but it's not labeled. If your data does not have clear labels of what does it contain, imagine you have a very large data file and you have no idea what's in the data file, you would use unsupervised learning to determine, to discover what's in the data. And again, we have the example from reinforcement learning, when raw data is fed into the agent. This is the agent, and the agent learns from selecting the algorithm, then determining the best action. If it's performing well, it gets the reward, the state, and then repeats the whole process again. The final result is the same, that you have a whole list of data outputs. Now we're going towards the second question. The second question, just as a reminder, was how do you optimize models with gradient descent? So this is the image that I designed. Let's look at how other people have described this. And for this, I'm going to be using an article which is in the list of references below from Monge. So first you have, let's say, the low alpha value. So you see how many iterations you have. So you have here 1, 2, 3, 4, 5, 6, 7, 8, 9. These loads of data iterations. So even though the loss is minimized, so you're going to reach this level here, the optimal, there's way too many steps. So this would take too long to train. Now let's look at the high alpha volume. So loss after the fourth iteration. So if this is when you're learning too fast, when there's less iteration. So you have the initial loss after the first iteration, and this is probably the closest that it gets, because the next one overshoots. So you're missing the point. So if you do add this step, as you can see on the gradient, you would be at the less effective state. That's if your model is training too fast. Then you have the optimal alpha value, where this is minimized with reasonable iterations. So here you would have, let's say, a more proportionate iterations. So that's 3, 4, 5, 6, 7, 8. Only 8 iterations. And in the first one, as you can see, we had a lot more than 8. So that's why this was not the ideal solution. So this is the optimal alpha value. And here we have a small animation of how the trick here is to reach the curve, and with different steps you're getting better and better towards the regression line to learn from the curve. So that's what these steps represent. Moving on to a different explanation of the same thing. So here we said that it overshoots, when some people prefer to describe this as the loss that is just very high learning rate. This is a different definition. explanation of the very same thing. When the high learning rate is overshoot, then you have the low learning rate, high learning rate, and then this is the good learning rate, because it's, as you can see, it's going towards the bottom of the slope over here. Now, this is a different paper, and this is explained differently, that you have the cost derivative, and the initial weight is here, and then you have steps that you're trying to perform towards reaching the local minima. So this is the best parameter that you're trying to reach. So it depends on how many steps you need to perform to reach there. But my favorite explanation of the gradient descent is this. Although it doesn't actually come from a journal paper, it comes from an article, news article, where the gradient descent is described as a widely used optimization approach in machine learning, and it's saying that there are different types of gradient descent, so batch, stochastic, and mini batch. So this is just explaining what those are. The gradient descent is an optimization approach for locating differentiable function within the local minimum. So, and the gradient descent is a technique for determining the values of the function's parameters that minimize a cost function to the greatest extent. It's built on the convex function and iteratively modifies the parameter to minimize the function of the local minimum. What does that mean? Let's explain this in one sentence. Einstein said if you cannot explain something in one simple sentence, it means that it's not clear to you. Gradient descent is basically the less steps that you have towards reaching the optimal lower point here. That means that the better model training that you have, because imagine that this would have to learn constantly in reinforcement learning on various different things interactively. You cannot repeat this process. It would cost too much to repeat this process over and over if you have way too many steps. In other words, if it's too perfect, maybe it's too costly, therefore it's not perfect. Now, moving to the third slide that we have here, which is the convolutional neural network architecture and the key components. This is the image that I prepared very quickly for you today. And these are more detailed images that other people have prepared to publish in journal papers. And the link to this paper, to this article, is in the list of references in the PowerPoint slides. But here we have the input, and then you have the kernel pooling, so then the convolutional kernel padding that leads to fully connected neural network, and then you get the dropout rate and the output. This is one explanation. If that makes sense to you, fine. If it doesn't, let's look at this from a different perspective, where the input is just an image of a zebra or a horse or something. Then this whole section here, from that whole section, is basically the feature extraction section, when you extract features from the image. So the pooling is basically a feature extraction section. Then you have classification section when it's using the fully connected layer, and then you have the probabilistic distribution, which is the output, and it's telling you, is this a horse, is it a zebra, is it a dog, and it gives you a different percentage points, 0.2, 0.7, 0.1. So it's very likely to be a zebra. Many people describe the fully connected layer as a ping pong tables. When you send the ball and you have to ping from one table, has to ping to another, and then reach to the final output, and then you know it's correct. Quite often, some of these the balls would lead into a different direction, and then you won't consider those as valid. Now, let's look at this from the same but slightly different connections. So we still have feature learning and classification, where the output section here is taken out, because those could be possibly the two most important sections. So you have input, then you have pooling when you use a feature, and then you have the classification when you decide if it's a car, if it's a truck, or if it's a van, or if it's a bicycle. Now, final explanation of the convolutional neural network before we close this short explanation is an image of a panda. And again, you have the feature extraction, the classification, and the probabilistic distribution. So you have Panda, and then you have the pooling stage, which is the feature extraction. Then you have the fully connected layer here, and then you have the output, and it's always described with the same kind of numerical representation. But now you know that this is, I don't want to print that, this is an image of a panda. That's in a nutshell the convolutional neural network architecture. These articles in the references that you can read to get more information, and there's also links to the journals that I have used in this specific presentation.